This is the second lecture for pericyclic reactions. So just a quick review before we begin. In the last lecture, we looked at electrocyclic pericyclic reactions. In that reactions, we had ring forming and ring opening because they are reversible reactions. That's the key. They are reversible. For sigmatropic reactions, pardon me, these reactions really involve effectively the movement of a sigma bond across conjugated systems. And of course, we discussed there two examples, which are the Cope rearrangement and the Claisen rearrangement. Don't forget to remember the names of these chemists because we tend to associate the names of different reactions that are discovered with the chemists or the scientists who discover these reactions. In this presentation, we will cover the following. Cycloadditions. So that's the last type of the three pericyclic reactions that we will be looking at, that's cycloaddition. And we will conclude by looking at some examples using the pericyclic reactions to solve different problems. So let's begin. So cycloadditions, this is the third type of pericyclic reactions. They are stereospecific. Notice the term stereospecific, in that a specific product is produced from a specific reactant. So let's look at this. So we have here ethylene reacting with cis. Notice the stereochemistry of the reactant butene to give a specific stereochemistry for the product, and this is cis 1,2-dimethyl cyclobutane. So notice again, it's an addition. So we're essentially adding these two molecules together to form a ring. So that's the key here, is the addition of two reactants to form a cyclic product. And notice they are stereospecific. We'll get more into that in a second. The other example is, notice this is a trans reactant and it gives a trans product. For these reactions, however, notice the energy that's supplied here is light. So that's important because we'll see some reactions require heat and some require light. So we'll have to look at why the difference. So let us look at the mechanism, or should I say the explanation, because as we said earlier, these reactions are concerted. They're one step. So we just go from reactant to products going through a single transition state. So there are no intermediates to say here's the mechanism. The mechanism or the explanation just involve electron movement in one step to form bonds. So the explanation that's used here is the molecular orbital theory. So let's look at how this occurs. So we'll have to look at the molecular orbitals for the pi bonds of both reactants. So here's reactant 1 and here's reactant 2. Looking at the reactions we did that was on the previous slide. Here is the pi molecular orbital. We have 2 electrons in the pi bond, and there are 2 pi bonds and bonding and an anti-bonding, or pi 1 and pi 2 star. We have 2 electrons, and as you know that the electrons occupy the lowest energy orbital first. Energy is increasing in this direction as shown here. So these two electrons here for the pi bond, they go into the lowest orbital here, pi 1, and that's described as the HOMO, as we've seen before, the highest occupied molecular orbital. This is now the LUMO, or the lowest unoccupied molecular orbital. Since there are two reactants, we have two that are similar here. One aspect here, however, is that electrons must flow from one reactant to the other one to form a bond. In other words, electrons must flow from the HOMO of one into the LUMO of the other to form this new bond. As we pointed out earlier, they must be phase correct, or the symmetry of the orbitals must be correct. Before I go to the next slide, however, I just want to point out here that the HOMO has this orbital. Notice the phasing here. Two shaded are on the same side, and the LUMO here for the other reactant, the phasing are different because the shaded ones are on opposite sides, higher in energy. Let's see the effect of that. So in terms of electron flow and meeting this requirement, you can see here that the phasing is incorrect if we use the HOMO of one reactant and with the hope of passing the electrons through to the LUMO of the other reactant. The phasing here, or should we say that the symmetry forbidden, that's another term that you'll see in your textbook, that is symmetry forbidden because the phasing here is incorrect. Now, how can we make it work? One aspect here is to look at one of the reactant and excite the electrons to go from the HOMO into the LUMO. As we saw in last lecture, this energy gap here is specific, requires a specific energy in light, and that energy comes from light. So in the presence of light, one electron here is promoted from the HOMO into the LUMO as shown here. So this orbital here now becomes the HOMO as the highest occupied. So now we have here the HOMO of one reactant, which has the orbitals here with the phasing here different from the HOMO of the ground state. So what that results in is that now we have the correct phase, or this is now symmetry allowed for electrons to move from the HOMO of one excited molecule into the LUMO of the other molecule, which is the ground state. So again, for this reaction to work, for electrons to flow from the HOMO into the LUMO, it requires excitation by light of one of the reactant so that this will be phase correct or symmetry allowed. So with that, what that means is, just illustrating that concept here using arrows, we have here one double bond and another double bond. Electrons flow to form here a diradical, and then it quickly, let's get rid of this here, then it quickly closes here to form the product. The stereochemistry here is maintained, as you will see here on the same side. But for this part of the lecture, however, just wanted to emphasize the requirements for energy to get this reaction to go. Same here. forming a bond here, the HOMO and the LUMO of the both reactants. One is excited, of course, and that's how the electrons flow to give the product here. So here's some reactions. So these are some reactions. These reactions are described as 2 plus 2. Why 2 plus 2? Because one reactant has 2 electrons and the other reactant has 2 electrons, 2 pi electrons to be more specific. So one reactant has 2 pi electrons and the other one has 2 pi electrons. So it's described as a 2 plus 2. Remember, for these pericyclic reactions, we are mainly concentrated on the pi electrons. So let's look at this. Here's 2 and here's a 2. In the presence of light, we'll have an excitation to make sure that the symmetry is allowed, and it will form a bond here between this carbon and this carbon and this carbon and this carbon. And here are the new bonds that are formed from the pi electrons. Notice again, the pi electrons now form sigma bonds, and they are shown here, and here's the cyclobutane structure. I should remind you again that these reactions are reversible, so it can go in this direction also, but we're concentrating now on just formation of the product. Here's another one, 2 plus 2, and presence of light, excitation, bond will form right here, and here is that bond, here's the other bond, so we have the cyclobutane here. Here's the last example, 2 plus 2, so now we're looking at this pi electron here reacting with this set of pi electrons here to form this bond here. So so what we're forming here is this bond and this bond here. So you can see there's a wide variety of possible combinations to give the 2 plus 2 cycloaddition product. Let us look now at the 4 plus 2. You can imagine what that should be. That means that one reactant will have 4 pi electrons in conjugation, and the other reactant will have 2 pi electrons. These reactions are referred to as the Diels-Alder reaction. Why? Because 2 German chemists, Otto Diels and Kurt Alder, discovered these reactions, and they got the Nobel Prize for their discovery. So as you can imagine, this is a very important discovery. So here's what it looks like. Here is the 4 in conjugation, and here's the 2. So it's a 4 plus 2, and in the presence of energy, we'll determine if this energy is heat or light in a second, but that gives us here that as the product. Let's just quickly visualize what should happen. So here is again the 4 plus 2. That looks like a typo here. So here is what should happen. These electrons should flow out to form a bond here. These electrons flow in to form a bond here. And these electrons flow here to form a pi bond right here. So we have a cyclohexene. As I pointed out earlier, there are no intermediates. There's just one transition state, and it's cyclic. Notice this cyclic transition state has 6 electrons, 2, 4, 6. So it's fairly stable based on Huckel's rule. So this is the explanation or brief electron movement to explain the 4 plus 2 cycloaddition pericyclic reaction. These reactions require heat and not light, as shown in the example here. So here is a 4 plus 2, and that's the Diels-Alder reaction. That's another name for these 4 plus 2 cycloaddition. As you can imagine here, using the same technique we have done before. These electrons flow out, these electrons flow in, these electrons flow here to form new bonds. So here are the new bonds right here and here, and of course the new pi bond. What I want to concentrate on now is why is it required? Why is heat required for this reaction and not light? So let us look again at the molecular orbitals of the reactants. The reactants are shown here. So this is the ground state. Notice the ground state, or the unexcited state of the 4 or the 1,3-butadiene. We have 4 pi orbitals, so therefore we should have 4 molecular orbitals, and they're shown here. You may recall that the ground state has the shaded are on the same side, and for the next one we have here 1 node. So notice there are no nodes here. Here's 1 node because we're going from unshaded over to shaded. Here we have 2 nodes. So we're going from here over to here and back over. And the last one has 3 nodes. Notice again, energy is going in this direction. So this is highest in energy and this is lowest in energy. There are 4 electrons in butadiene. So of course, as you know, only 2 electrons per orbital. So here 2 and here 2, making 4 electrons for butadiene. As we know, this is the HOMO and this is the LUMO. Now you know why we are emphasizing the HOMO and LUMO, because the electrons flow from the HOMO of one reactant into the LUMO of the other reactant. And of course, as we know, it must be phase allowed. Let's look at the ground state of the other reactant, ethylene, which has 2 pi electrons and hence 2 molecular orbitals, or pi molecular orbitals. Here's pi 1 and pi 2, 2 electrons. Energy again is going in this direction. So this is the lowest molecular orbital, pi molecular orbital, and we have 2 electrons here. This is the HOMO and this is the LUMO. So for this reaction to work, electrons must flow from the HOMO of one into the LUMO of the other, and most important, or equally important, they must be phase allowed. So let us look at the ends of these orbitals, sometimes referred to as the frontier molecular orbital. So here's this carbon for the butadiene, here's the other carbon. Notice the phasing here and here. Let's look at the LUMO for the ethylene. This is it, frontier orbital, so right here. Notice the phasing. So this is unshaded and this is shaded. So it looks as if the phase will work if electrons are to flow from the HOMO of one into the LUMO of the other. The next slide has that illustration. So let's look at this. So here's the butadiene. You can see here shaded and unshaded for the ends, or the frontier ends. And here is the LUMO for the ethylene. You can see here shaded and unshaded. So these are symmetry allowed because the phasing are now correct. So that is why we need not excite an electron to get another orbital, or the highest molecular orbital, with a different phase for this reaction to work. It works with the ground state orbitals. Ground state orbitals. So what's required here is just heat and not specific energy such as light. So here are some examples of the Diels-Alder reaction. or the 4+2 cycloaddition reactions. So here's the 4 and 2. So as you can imagine, here we can use electron to arrows to show electron movement, and we can do that, and here to show the electron movement to form this as the product. Same here, to get that as a product. Here's a tricky one. Here's a diene, this is the 4 and the 2, but this is a cyclic molecule, so when you do the electron movement here, you get a bond forming between these two carbons here, and here they are, but the bridge is now right here. So it's just drawn a little differently, showing the bridge for that bicyclic compound. Notice this is a bicyclic, 2 cycles, 2 rings to make the product. Let us look at substituent on the diene and the dienophile. So it was discovered based on different experiments that for effective electron flow, it's best to have electron-rich diene and electron-poor dienophile. So in other words, the diene should be electron-rich. That's the diene. And the dienophile should be electron-poor. What do we mean by that? So let's look at this one here. So this is electron-rich because it has electron-donating groups here. Well, at least one electron-donating group here in terms of the methoxy. You will recall that the methoxy is electron-donating when you looked at the substituent effect table. So this is electron-rich, and it's been shown that this reaction works much better with the electron donating group on the diene. Here's an electron poor dienophile. Here's a CN. Remember that C triple bond to N. So it's pulling electrons into the nitrogen, so it's electron poor because it's pulling the electrons away from the dienophile. And that's been shown to be effective if we have electron poor dienophile. Let's see why, or one explanation for this. Here is the molecular orbitals, just showing here the HOMO and the LUMO for the diene and the dienophile. So as we pointed out, electrons flow from the HOMO, highest occupied molecular orbitals, into the lowest unoccupied molecular orbital of the dienophile. So if there are electron donating groups on the diene, notice we put electron donating, so we're putting electrons into a orbital that already has electron. That raises the energy. As you can see here, the energy is raised. Energy goes in this direction, as we have seen before. So this goes up if we have electron donating group. If we have electron withdrawing group on the dienophile, that means that we are taking electrons away, which means that it's much better to put electrons in so that energy is lowered. So the main point here is the gap between the HOMO and the LUMO. Let's call that delta E. You want that to be as small as possible. Less energy is required for the electron transfer. So if this gap is small, the reaction is very favorable. So electron donating group raises this here. Electron accepting group lowers this gap here, which makes, of course, well, let's put it here, lowers this gap over here, which makes this gap here much smaller. So we have electron flow from the HOMO of the diene to the LUMO of the dienophile, making for an effective reaction. Let us look at another aspect of this reaction. They are in fact regioselective. That's another term that we covered earlier when we did our stereochemistry lecture. So a regioselective reaction here gives a specific product. And it's typically for stereochemistry, but this is regio, which means a particular region. So notice here for this molecule here, this diene, and we have the dienophile here, we get two possible products, because we can have the bonds coming out here and we have this as a product. But if you flip this molecule here, just well, let's put it like this. If you flip this molecule here like this and react it with this, you can see that you will get this as the product. However, this is the minor product and this is the major product. As a good chemist and a good scientist, we have to have an explanation as to why this is the major product here and this is the minor product for the regioselectivity for these reactions. Let's see if we can explain that. We can explain this using resonance structures. So let's look again at the diene. This is an electron donating group, as we have said earlier. So it pushes electrons into this carbon here, and here's the resonance structure. Let's look at the dienophile. This is an electron withdrawing group. So it pulls electrons from the dienophile here, or the two electrons are pulled out into the oxygen. So as you can see here, this makes for a very effective reaction where the negative from the resonance structure reacts with the positive of the resonance structure for the dienophile to make for a very effective bond forming to form this product as a major product. Let's look at the reverse, or the flipping the molecule. So if you flip the molecule as we have done before, shown here, and draw the same resonance structure, this is what we have, but here is the negative, but notice it's now reacting with this and not the positive, because this is pushing electrons back here. As of course, as you can see here, the electrons going into a negative region will not be an effective reaction because like charges will repel. Same here, this is positive and these electrons are moving away, so a positive will not react with a region of the molecule where the electrons are moving away from it. So this is not formed, or if formed, is the very minor product. So again, these reactions are regioselective because a particular region of the molecule, the product is specific for a specific region of the molecule. So let's look at some examples here. So if you ask to predict the major product for these reactions, let's look at this. So again, this is the 4 and the 2, or this is the diene and the dienophile. Just to refresh your memory, the diene means electron loving, and the dienophile means that it loves the electron. So the dienophile is positive, or they essentially love electrons, and the diene wants to give electrons. So in the presence of heat, notice again this is heat and not light, because this is the 4+2 reaction. Here's the product. Notice the relationship. It's a 1,4 relationship that we have explained before. So this is now the major product. Right? And not the 1,3. Here again, even though this is written a little differently, but this is still the 4 plus 2. And now we will not get the reaction product, the region of the product here, but here, because as we illustrated earlier, this is electron donating, this is electron withdrawing, and it will give here the 1,4 as the product. So look out for that in terms of predicting the products for these reactions. These reactions are also stereospecific. Notice again, stereospecific here means that there's a specific reactant that's required to give a specific product. So it has to deal with the reactant, the stereochemistry of the reactant, and the stereochemistry of the product that's produced, and that's called a stereospecific reaction. Let's look at this. Here's the dienophile, and here's the diene, so that's a 4 plus 2. But look at the stereochemistry of this reaction here. The two methyl groups here are on the opposite sides, are on the same side of the double bond. So here's the double bond here, they're on the outside. Here's a double bond here, they're on the outside. So that's one way of looking at it. They're on the same side of this conjugated system, on the outside. In the presence of heat, they remain on the outside. So we get here the methyl group, or whatever group here, is a substituent on the same side, so it gives a cis product. Notice it could be written either with a dashed or a wedge or a dash, but it's on the same side in the product because they're on the same side of the conjugated system in the reactant. That makes it for a stereospecific reaction. Let's look at the opposite. Now the diene, the one methyl group, is on the outside, so to speak, of the conjugated system, and the other group is on the inside, so to speak, of the conjugated system. So they will be on different sides of the conjugated system. Hence, in the presence of heat, we have a 4 plus 2, or a Diels-Alder reaction. And notice now that the methyl groups are on the opposite sides in the product, trans, because they are on opposite sides of the conjugated system in the reactant, again making for a stereospecific reactions. So as a summary, the Diels-Alder reactions are in fact stereospecific. They are regioselective also, as we've seen from the previous slide. Let's look at some examples here. So here is the 4 plus 2. These are the 4, 1, 2, 3, 4 pi electrons, 2 pi electrons. Notice the stereochemistry. These are on the same side of the double bond, and so therefore this product here shows the CN on the same side in the product. That's stereospecific. Again, we have here same side of the double bond. Notice again, this is the diene, but it has a bridge. It's cyclic, so you can see that it will generate a bridge here to give the bicyclic product. Here's another one. So this is written a little differently here, but it's basically the same as this molecule here, the cyclohexadiene. Just taking this bridge here and put it up. And that's just done to illustrate that the bond formation is really here and here and here, as you can see here. So the bridge is still here, and here's the product. So notice again that this is on the endo side of the bridge, because this bridge is occupying the top of this reaction. This group here goes on the bottom side of that. Well, two products here, the bottom side on the top side. So this is a major product here where this is occupied on one side. We just keep it for that for the time being. So this group here is on one side of the bridge. Okay, let's look here at some examples to conclude this lecture here. So shown below is a reaction. So here's the reactant and it goes to the product. So it's been shown that there are two pericyclic reactions involved to make this conversion. The first is an electrocyclic ring opening. Remember, electrocyclic ring opening, electrocyclic reactions were done in the previous lecture. Okay, and the second reaction is now the 4+2 cycloaddition reaction. So let's see if we can figure that out. So here's a cyclobutane right here. So it seems as if there's an electrocyclic ring opening of this here. Let's see if we can do that. So it seems as if this goes here first, and then there is, so that creates a conjugated system, and then there is a 4+2 with what results. So that's a little difficult to see, so let's do it step by step using the two different reactions. The first reaction here is this. So here's a cyclobutene. Opening this up, we get this, which, if that's an electrocyclic ring opening, remember those reactions are reversible. So you can close it by going in this direction, or you can open it going in that direction. Another way of drawing it is like that, very huge cyclic compound. But notice here though that there are 3 double bonds in conjugation. So if we can get a 4+2 out of this, we have the product. So here's our 4 and our 2. So this would form, using this to show the electron movement, we have this as the product, or drawn differently like this, which is the product shown. So again, here's the electrocyclic ring opening, and here's the 4+2. These are the type cycloaddition to form a ring. Let's look at another example here. For the synthesis of the sex hormone estrogen, shown here, the two sequences of pericyclic reactions. The first is again an electrocyclic ring opening to form an intermediate A, and the second is a 4+2 cycloaddition to form the product. Let's see if we can visualize what's happening here. So here is again our cyclobutene. So we can imagine here a ring opening, one here and one here. So once you open that up, you'll see that you'll have here a conjugated system, and here is a potential dienophile right here. So once this opens up, this can react with this to close that ring. So let's look at it step by step in terms of the reactions. So again, here is the ring opening for the electrocyclic reaction, and this is it. Okay, so that's the intermediate. That would be the intermediate. But notice again that this intermediate here, let's look at it down here, is set up to do a 4+2. So here's the 4 and the 2. So if these electrons came out here, from here, come back in here, we have this as our product. So you can see here that we've formed new bonds using this as our 4 + 2 to get that 4+2 cycloaddition to give this as the product. So again, hopefully you can appreciate some of the chemistry here for the pericyclic reactions. They're very useful in, as you can see, for natural product chemistry, in making these products here, and very useful reactions in making, especially the cycloaddition, in making 6-membered rings, as we have seen here for the formation of this 6-membered ring here from this right here. So they're very useful in forming 6-membered rings. And of course, as you know, in nature, a lot of the natural products are in fact 6-membered rings. So that's why these reactions are so important in chemistry. So this is the last lecture of the course. It was great working with you for the semester, but continue studying, and as you get prepared for the final exam. Remember, the final exam will be comprehensive, so it will cover this and everything we've covered throughout the course. But I will communicate with everyone with an email shortly with more details. So continue to study hard, and all the best. Bye-bye.